Has this ever happened to you? You want to implement some kind of DSP effect and you're searching Google for code and you just can't find any? You might find some scientific papers with some equations and some block diagrams. So in this video, I'm going to show you my method and my thought process of how I translate that stuff into code. If you don't know me, I'm Landon. I'm an audio plugin developer and I upload tutorial videos on C++ and audio coding. All right, let's jump in. Okay, so I've got this project up and built already. It's an audio plugin, and I already have a scaffolding for processing some audio stuff. So all we're gonna have to do is place the code inside of this class, and he gives us a block diagram to implement this class. We have a positive signal path right here, and then the bottom is a negative signal path. We have 4 wave shapers and 2 high pass filters acting as DC filters. Now in the paper, he describes what this wave shaper is, and if we scroll up, this is the equation that describes that wave shaper. And all we have to do is implement it in the code. Now, when you see equations in DSP papers or math papers or engineering papers, usually your yn is going to be your output and your xn is going to be your input. All right, let's jump to CLion and see what this looks like. Like I said, we're going to start with that wave shaper, and then we're going to work through the block diagram after. Okay, let's write a method. Let's call it process wave shaper. And we're going to need to take in the same amount of variables as the equation. So we need our input, which is xn, our k, which is gain, and then we're going to have this limit negative and limit positive. And if you read the paragraphs before and after, it describes what these values are. On the second page, it actually gives us some values to work with for those, so we don't even have to guess on that. All right, let's add our arguments. Okay, that's everything we need for this equation. And all we're going to do is basically just rewrite the equation in C++. Okay, so when the input is negative, we do this part of the equation. And when the input is positive, we do this part. So let's start with that. Let's start with separating our signal. Okay, so let's check to see if our input is positive. And if it is, we'll put the positive stuff in this block. And if not, we'll do the negative stuff. And let's see if we can break this up even further. We have this repetition right here, k times xn. We see that 4 times. So let's just put that into a variable. Let's call it the numerator. Okay, so if it's positive, we are going to divide this section by the numerator. Let's use yn as our output, divided by. Okay, does that match up? We've got our numerator, which is kxn, divided by 1 plus numerator divided by, oh, it's supposed to be LP. Ln is for the negative path, so let's do that one. Now that we have this, we can just copy and paste it. Numerator, and this is going to be minus instead of plus, and this is going to be Ln instead of LP. And that's it. And we return that. And that is the wave shaper done. Okay, so let's get to this block diagram. So similar to the wave shaper, we're going to split this into 2 signals, and let's create a method for it. We are going to need only 3 arguments for this one. Input, drive, and we're also going to take in the channel index. We'll need that for these high pass filters. All right, so let's make 2 variables to hold our positive and negative signal. Okay, so float xn positive and float xn negative. What we'll do is another if statement. Let's not forget our arguments. We need xn and k. And then we also need channel. All right, so if xn greater than or equal to 0, xn positive is equal to xn. And then as you can guess, we're going to do the same thing in the else block, but we're going to assign negative. And some of you might see that this isn't the best way to go about it, but I'm going to show you how to follow the path in the most direct way possible. So I'm just going to do the exact same thing that the equation and the block diagrams are doing. I got a piecewise condition branch. I'm going to do it again for this one, and then we can optimize it later. Okay, so now we have our positive and negative signal separated. So what do we need to do? We need to take the positive one and pass it through the waveshaper. And you can see that it says asymmetrical for these and symmetrical for these. So if you read the paper, it says that all waveshapers share the same equations but use different coefficients. The symmetrical version has ln equal LP. So if we pass in the same values for ln and LP, we get a symmetrical waveshaper, and if we don't, we get the asymmetrical one. So let's do that. Xn positive is equal to process waveshaper, and it's going to be Xn positive as our input, the dry, which is K, and then LP, which if we look at the paper, he suggested 6.6 for LP and 0.6 for LN. So that is this block done. So let's do the negative block. It's going to be very similar, but we're going to take negative and pass that into it. And then we need to flip around these values. Okay, now we just need our high pass filters, which isn't difficult. We're just going to use some of the juice filters. So we need 2 of them because we need 1 for each channel. So we're going to use the Linkwitz-Riley filters, and we need 2 of them for the positive one and 2 for the negative. Okay, we just have to set those up, which isn't too difficult. We're going to go into our prepare function. I'm just going to initialize both of them in one loop. So we'll take the positive ones and we'll say prepare, and we'll pass it in spec, which we're already getting in our prepare method. And then we need to call set type to set the type of filter we want, and we want a high pass. Linkwitz-Riley filter type. Then we go into it and get high pass. And lastly, we need to set the cutoff, which you can put whatever you want. I think usually you would use 5 hertz for a DC filter, but you could do 10, you could even do 20. Now we just need to copy this and do the same thing for the negative ones. So let's just grab that right here. Okay, excellent. We're done with that. That should work. So now we can go back into the Paletti method, and we are going to take the positive one, take our positive signal, and say that is equal to M positive DC filters. And which one do we want? We want the one for the channel we're on. And we're going to say process sample, and we need to pass in channel and the thing we want to filter, which is that positive signal. Okay, we just need to do the same thing for the negative. So let's grab negative right here, and then we need the negative filter. Okay, that's looking pretty good. All right, let's take a look back at the paper. So we've got this point done, this point, and we've got this point done and this point. Now, this right here is a suggestion that Will Perkle made, that you could stop right here, grab the output of just this 2/3 of the diagram, and then save that into a variable, and then do your symmetrical wave shaping and take that output and add it to this one. I didn't really feel like it sounded any different, so I'm just going to implement the block diagram as a whole. So let's go to our symmetrical wave shaper part. And remember what we need for that. We just take the same equations and we make them symmetrical. So we pass in the same values for each one. Now, he doesn't describe what a good number for that is, but I messed around with it for a little while and found that 1.6 worked pretty good. So these all need to be the same. And now we just need to sum those together and send it out. So Xn positive plus Xn negative. And we already have all the scaffolding for setting the drive and stuff like that. So we've got our 2 methods. So let's just call it in our block right here. So this is going to be process Paletti, and it wants the input, the drive, the channel. Okay, so we're saying yn is equal to that entire setup we just made, and we're sending it out. And I already have drives set up, so we have a fader that we can push up or down, and I think we're ready to test it. So this is what the wave shape is supposed to kind of look like. At different gain values, this was the highest gain value that he used. You should see this crossover distortion right here where the little bumps are on the sides. So let's see what we get. I'm going to build it real quick. Okay, I'm going to open up in Plugin Doctor because it has an oscilloscope, and let's load our plugin in there. Okay, you can see we have our drive fader right here. Okay, let's see, how's it looking? There's our waveform. Okay, there we go. It's not perfect, but it's pretty similar. Now that's right, he said that he tested with a cutoff or with a frequency of 150 hertz. So let's try that. Not sure if it'll make a difference, but let's check it out. Okay, there we go. Looks pretty good to me. So there's a lot of things we can do to improve this. For example, you can see the signal starts out a little bit lower in volume than the input. It comes down by about 0.4 in gain, and then when you turn the drive up, it gets pretty loud. We could do some kind of automatic compensation for that. But first, let's try to get rid of these if statements. So if we go to our main process loop, we're processing through each channel and we're processing through each sample. And then we're calling the process Paletti on each sample. Now, if statements with branches in your sample by sample loop is not good. It's going to be slow. And that's because your CPU, when it sees a conditional, is going to try to predict based on the input whether it's going to follow the if branch or the else branch. And since it is relying on the audio, which is coming in from outside of the plugin, it can't really predict whether it's going to be negative or positive. I say negative and positive because that's what we're checking. So it's going to be wrong half of the time at least. So that means that the if branch is going to be pretty slow. So if we can use a little math trick or some other way to divide up the if statements, that would give us some increased speed and our algorithm would be a little bit better. Okay, so to get rid of this if-else branch, we are going to do a mask pattern. Okay, so let's do this. We are going to make two floats. X positive, which is equal to this. And as you can probably guess, we're going to make the negative version. And obviously, if we used another if statement to just pick which one we send out, that's not going to help us at all because we're still going to have a branch. Okay, so we're going to create what's called a mask. And this is just going to be a float that represents 0 or 1. So we'll say static cast. Don't know why it's not auto-completing. Oh, because I didn't put a name. Mask is equal to static cast to float. And this is just going to be x in greater than or equal to 0. So this is a conditional, but it doesn't branch. It doesn't get separate instructions to follow if it's true or if it's false. So that's fine. And we're going to use that to kind of mix between the negative and positive signal. So we're going to say x negative plus x positive minus x negative. and that's going to be multiplied by the mask. So what this is going to do is if it's negative, mask is going to be 0. So this part will be multiplied by 0 and we'll only get the negative. But if the mask is positive, we're going to get 1. So that's going to be negative plus a negative, which is going to equal positive. Let's just build that and make sure it actually works. Okay, it looks like it might still be good. Yes, okay, the shape is still correct. Very good. So for the Paletti, we don't even actually really need to change anything. Since the waveshaper is taking care of the negative and positive part for us, we can just say float and float, get rid of this. Yeah, and then we can just pass in xn here. And passing in the correct ln or lp, positive or negative variable, will perform that part of the equation. So I think we can just leave it like this. No if statement. Let's build it. Still looks good. Let's see. Let's make sure. And excellent. We are still getting the same shape. Everything looks great. Okay, good. We could use a mix trick to make this more subtle, and that would also help our volume difference. Okay, so our gain is coming in at 0 to 10, and that is being scaled by decibel, so it's really 0 to 3. Yeah, so let's make a variable called mix, and we're going to set that equal to, and we're just going to map this. So K right now is from 1 to 3.1-ish. So we're going to map that to 0 to 1. And we're just going to use that to mix our output with our input. Okay, so our output yn is equal to this. So let's mix it. We're going to say 1 minus mix, and that's going to be multiplied against the dry input, so xn, and we're going to do plus yn times mix. So that when mix is 0, 1 minus 0 is 1. So we're going to do 1 times our dry input, so no change, and then 0 times our wet input, so no wet, and then the opposite is going to be true for the other direction. Let's see how it actually works out. All right, cool, no change, and that's correct because our mix should be at 0. All right, let's see. Okay, cool. All right, so that's a little better. We still get the full distorted signal at a drive of 10, but it starts with our signal unchanged and not reduced by any amount, and then it kind of slowly grows, which is to be expected. Most people expect for the volume to increase whenever you drive something higher, so that's cool. All right, I think that's good for now. That'll about do it. All right, I hope that was helpful. Feel free to leave a comment if I skipped over something or breezed over something too quick. Join the Discord, which will be in the description of the video, and I'll see you in the next one.